Okay. Hi, everyone. Thanks for being back. I hope you had a nice coffee break, even if short. We apologize for that. So it's an honor to have Rareș here with us. So Rareș is a research manager at the Large Behavior Model division at Toyota Research Institute. And his research spans robotics, machine learning, and perception, and in particularly emphasizes extracting visual representation for embodied agent. Prior joining TRI, he obtained his PhD at KTH, Royal Institute of Technology, where he worked on self-supervised perception and mobile navigation. So, Rareș, the floor is yours.
Awesome, thank you so much. Can everybody hear me? Yes, okay. Sorry about the technical difficulties. I think, there's always something in the beginning of these presentations, and I hate to be the person to be between everybody and their lunch. But I think we're good to go now. Seems like the slides are showing, Zoom is working. So it's awesome to be here. I'm going to tell you about our work on building structured large behavior models for dexterous manipulation. And this presentation is going to be split into two different parts. First, I'll talk about our work building LBMs, large behavior models, what they are, how do we evaluate them. I'll show you some cool tasks, and I'll use this as a way to highlight some of the cool results we can get with them, as well as some of their limitations. And I'll use that as a way to motivate the second part of the talk, which is going to be about adding structure and inheriting some priors from other large-scale foundation models. Okay, I guess I don't really need to motivate this, but we want our robots to do cool things, dexterous things. We want them to help us in our daily lives, in homes, in supermarkets, in factories. We want them to be able to do dexterous tasks and to have common sense and generalization. And systems today, they don't really generalize across semantic categories. You have to sort of train them on lots of different data, and they have lots of different limitations. And the reason why we don't really have these robots in our homes today is because dexterous manipulation is really hard. Here's an example of a typical living room, not mine on a normal day, but sometimes. And this is just as a way to highlight some of the challenges that we have to deal with. There are occlusions, lighting variations, various kinds of safety requirements, clutter, object variations, physical constraints, and so on. And robots, for them to be able to work in home environments, they have to be able to deal with all of these things. And importantly, what they need is common sense, the ability to generalize across various kinds of categories, and also dexterity. And I want to take a second and define dexterity. So we've been thinking about this for a while at TRI. And when I say dexterity, what I think about is tasks that involve lots of contact, tool use, multi-arm coordination, precision. And here's an example of a particular task that I would say is sort of a dexterous task that I would want robots to be able to do. In this case, the robot has to unzip the Ziploc bag, lift it up, pour the contents from the bag into a bowl, and I would want it to do this autonomously. Okay, getting there. Yeah, so that's an example of a dexterous task. It would be great to have a robot in our homes who could do something like this. Another thing that I care about is long horizon. So robots should be able to do things and that are not just atomic operations, but over a few seconds or even minutes. So here, the robot is packing this picnic box. It puts, the most important things that we care about when we go on a picnic, a couple of Coke cans and some ice. But anyway, you get the idea. It has to pick something up with one hand, put it on the table, pick it up with the other hand, put it in the box. And so it's sort of long horizon dexterous task, which is another thing that we care about. Okay, so I'm going to give you just a brief overview about how we get these models to be able to achieve these tasks. So we start from diffusion policy, which is kind of a general recipe for behavior cloning. I think everybody's aware with the general setup, and diffusion policy was published a couple of years ago, and it really kicked in a new era of dexterous capabilities. And the setup looks something like this. We have an expert operator collect a bunch of demonstrations with a joystick or a space mouse or something like that, and this forms our data set. And we have images paired with robot actions, and we use the images as input. They're the observations along with the robot state, pass them to an encoder, and we use a diffusion decoder to generate actions that the robot can execute. And diffusion is awesome because it can capture multimodality, and it really enables dexterous kind of operation. All right, and there are some limitations, and fundamentally with diffusion policy in the single task setting, we basically have to learn everything from scratch. And that's obviously brittle. If there are environment variations, then we can't easily adapt to those. If we want to, say, learn how to manipulate an apple, and then we want to transfer that to an orange, that's not going to really work out of the box. And really what you get is what you teach. And if you want generalization, you have to add more demonstrations. And out of the box, you don't really get transfer very easily. And what we're interested in studying is how do we transfer dexterous capabilities from one task to another task, and how do they improve with these large behavior models? Okay, and I'm going to give you an example of particular model or class of models that we've been studying for quite a while at TRI. So we started with diffusion policy, which is kind of a well-known and understood recipe, and we scaled it up in the multitask setting. This is an example architecture. We basically did a couple of key modifications to go from the standard single task diffusion policy to multitask. We basically added the language encoder. We replaced the ResNet encoders with clip VIT. We concatenate everything. We pass everything to a diffusion transformer. So we got rid of the unit. It's not much larger, but it's something that is easy to study, and we know it has some limitations. But it's something that we understand fairly well. About 450 million parameters, so not huge. And it can be trained fairly fast. And this is one class of models for multitask behavior cloning. There are others. We know VLAs are sort of popular in the literature, and they borrow priors from pre-trained vision language models. There are also video LBMs, which is what I'll talk about in the second part of the presentation. And in the beginning, I'll just give you an overview of these kind of LBMs that are sort of scaled up diffusion policy and some of the tasks and limitations that we found with them. Okay, so we take an architecture like that. We've collected a fairly large data set, so 500 skills, roughly 500 hours, combination of sim and real. We have a mix of short horizon skills and long horizon skills, and we focus on high quality data. So this is an example. A combination of pick and place and more dexterous tasks, and this is what forms the training data set that we collected. And we combine this with external data from the internet. So we looked at the OXC data set. We don't use all of it. We use a subset. It's fairly larger than what we've collected, so we do a batch balancing step. And that's what we use to train the network. And we oversample our own data because we think that it's going to transfer better to our own platforms because, of course, we collected it with the same platforms. And also because we think it's a sort of slightly higher quality in terms of calibration and things like that. Okay, there are many different ways to study these LBMs, and we have lots of different results that we're writing up in a paper that we'll put on arXiv. For now, I'm going to focus on this particular setting where we basically start with a base model with initialized encoders. We train this model on the robot data that we collected in combination with the internet data that I mentioned just now, and we get a pre-trained generalist. We take that model, we look at an unseen task, we fine-tune it for that task, and then we get a fine-tuned specialist, and I'm going to talk a little bit about the capabilities of this fine-tuned specialist on some tasks that we designed. Before we get to some results and videos of robots doing cool things, a little bit about how we evaluate. So for each task, we do blind A/B tests in real, and we have controlled initial conditions. And the reason we do that is because there are sort of variations in the real world that we can't really control. For example, we might take a method, evaluate it, Monday this week, get 70%. evaluate it Monday again, 2 weeks from now, get 60%, and we have no idea why the performance difference. It could be that someone bumped into the camera, or we evaluated in the morning first, and now it's afternoon, and things like that we can't really control. So we do A/B tests, and we always compare our method with the baseline whenever we do experiments. Initial conditions is something that we design beforehand. So whenever we do a rollout in the real world, we specify this is the environment, these are the objects, this is how they should be positioned, and we have an overlay where an operator looks at the scene right now, the initial condition, the way it should be, and the operator sort of arranges things so that we know we control exactly for the experiment, and we can run both our method and the baseline under the same kind of conditions. And because we control things, we can also vary the initial conditions quite a bit. So this is an example for some simple tasks that we evaluate on. We change the object significantly, and then we can really look at performance along a few key axes that we care about in terms of robustness and generalization. Okay, so I'll show you a few tasks that we came up with, and the goal is to really push the capabilities of the robot in terms of dexterity and long horizon. And we wanted to find a balance between something that is very difficult, but that the robot can still execute and get some amount of success rate. So we don't want to be at 100% success rate. We also don't want to be at 0% success rate, because it's tough to learn anything in the extremes. We want to be sort of in between 20, 30%, something like that. Okay. So here's an example of a fine-tuned long horizon task. You'll see the LBM on the right and the baseline that we compare against, the single task on the left. This is a long horizon task where the robot basically has to set a breakfast table. And it looks like a bunch of individual skills, but actually the whole task is sort of demonstrated as one continuous demonstration. And then the robot has to learn how to execute it. This is the set breakfast table task. And we see that the LBM is sort of generally more dexterous. It doesn't always succeed very well, so it keeps trying to pick up the apple. But based on introspection, we find that even when it fails sort of more gracefully, and then it learns how to recover, and it keeps trying in a way that is more natural than the single task baseline, which is which still executes the task, but it's generally less accurate, and sometimes just fails. Okay, that's one example. Let's look at another example. This is maybe one of my favorite tasks. So this is autonomous, by the way. We pre-trained the LBM, then we fine-tuned it for this task, and then we let it execute. This is, whenever I see this video, I'm kind of impressed that the robot can do this. So basically, we have a bike tire, and the robot has to pick up this rotor and put it on the tire, and then tighten the a bolt with the spanner. And so you saw it dropped it by mistake, and then it went and it picked it up. And this is all autonomous, sort of learned from data, these recovery behaviors. And now it's going to try to fit it in, pick up the small part. Okay, fit the small part. There's quite a bit of moving around to do to make sure that it doesn't fall, which, by the way, happens quite often. But sometimes it succeeds. Okay, then it's going to put the spanner and then tighten this bolt. So this is an example of a task that requires not just long horizon execution, but also quite a lot of precision, right? Okay, I'll move forward to show you one more, which is also quite impressive, I think. So here the robot has to cut this apple in slices. And first it has to remove the core. So we call it the apple coring task. This is also autonomous, by the way. So it's the same LBM baseline model that's fine-tuned for each one of these tasks, and then we let it execute it. Okay, it's going to pick up the knife. Yeah, there was a lot of fruit wastage that day, but, and yeah, I mean, there are many delicate steps. It has to take the knife out of the sheet. It has to cut the apple in half, turn it around, slice it. but generally it looks like we're seeing some very interesting signs of life in terms of dexterity and pushing the boundaries of what these robots can do. Okay, it's going to slice it, then move it to the side. Okay, slice the next one. You get the idea. Okay, so qualitatively, it looks very impressive and very interesting. Those are sort of some of the better rollouts. When it fails, it's not, it keeps trying in a way which is natural, which is very interesting. So we're trying to introspect and analyze exactly where those behaviors come from, how to incentivize the model to learn more recovery. We also have quantitative numbers. So this is a way to show success rate, these violin plots. I'll go a little bit through the details of what's happening here. On the x-axis, we have a few of these long horizon tasks that we designed to be sort of complex and difficult. On the y-axis, we have the success rate. The violin plots are a way to show the posterior over the success rate, and the success rate is the parameter P of the Bernoulli distribution that generates success failure. So we do a Bayesian analysis. I think it's more informative than just box plots with confidence intervals. And we also look at task progress, which is basically generated by having an operator look at the rollouts and saying, okay, in this case, the robot did 5 out of 7 steps, so we get whatever success or task completion metric. And so on the left, we see the success rate is as expected, in some cases around 40%, in some cases around 10%. But anyway, we're seeing the robot starting to execute these tasks reliably. And despite the slightly low success rate, in terms of task progress, we get quite far into the task, both the baseline and the LBMs. Okay, going to change gears a little bit and tell you a little bit about new and exciting work where we're trying to basically overcome some of the limitations we're seeing with LBMs. So if we take a look at these results again, we see that success rate is quite low. This is, it makes sense. We designed these tasks to be difficult, and we are, of course, trying to improve the model to get better success rate, get better at executing these tasks. And we know we have to think of ways to deal with dynamics in the scene, because these tasks can be quite complex, long horizon, occlusions, contact, geometry, and so on. Another thing that I didn't mention here, but a known limitation, is if we try to evaluate the generalist model, so the LBM out of the box without fine-tuning, it doesn't really transfer to these long horizon tasks. So this is also something we're looking into, and something that we hope to get out of structured large-scale foundation models. And to overcome some of these limitations, we started looking at video models for robot learning. And we look at recent advances in video generative models like Google VO2 here, or OpenAI Sora. And we see that they're quite impressive, and they highlight like very exciting advancements in building foundational models that capture dynamics and the effect of actions in the real world. And this is something that we want to evaluate and introspect and see how can we transfer these priors to actions. And we've put together a paper which is actually under review, and it's kind of early work in this direction. It's called Video Generators Are Robust Robot Policies. It's in collaboration with colleagues from Columbia University. And we investigate how to combine video generation and action generation in a modular framework that can be trained end-to-end. And I'm going to tell you a little bit about how this is set up and early results, which look pretty exciting, I think. So the goal of the paper is to see if we can turn video generative models into policies. And we actually show that the video models already have quite a bit of information, and they can easily be adapted to be policy generators. And not only they can output actions, but they also generalize in very interesting ways to new environment configurations, new objects, and also new tasks, which is something that we hope to borrow and that we'll use to improve our LBMs as well. Okay, so here I'm going to show you an example. The rollout is on the top, and the video prediction, so this is the output of the video generating model, is on the bottom. There will be more videos. The video generation models takes about 7 seconds for inference, so that's why it sort of looks a bit out of sync. But generally, it follows the rollout and the execution trajectory quite well. So just a very brief overview about how this works. As before, we start with a set of demonstrations, which we collect. This forms our data set. We have paired images and actions. We use the images to fine-tune this a video diffusion model, which we have. We use it pre-trained. We use stable video diffusion here. We extend it to also take language conditioning, so we can steer it with respect to a particular task. And then we have it generate video based on the first frame and the task. And at the same time, we train a video adapter and an action decoder, either jointly or afterwards. And we condition this with noise, and then we generate actions which can be executed on the robot. We use RoboCasa first for evaluation and simulation, which is great. We can do lots of experiments. People who have used RoboCasa are familiar probably with the setting 24 sort of atomic tasks that we use to benchmark the performance. We use the standard benchmark. We use only the 50. So there are many different settings. We use sort of a restricted regime in terms of demonstrations. We compare with a few state-of-the-art published methods. And it seems like our method works quite well, even though we use few demonstrations. DP-ResNet and DP-Clip are sort of baselines that we implemented. They're just vanilla diffusion policies scaled up for multitask. And we have a few very interesting results in addition to this that I'll go into, which I think highlight the power of these models and the kind of transfer that we get from them. So in addition to the average results, we looked at why does this work and how well does it work, and what's the interplay between action and video generation. So we looked at a few different ways of training this model. So on the bottom, if we don't do any video training, then it doesn't really work so well. It doesn't generalize. So we can't just add an action decoder on top of a video generating network. Out of the box, it doesn't really conditioned on our images from RoboCasa. It doesn't really generate high quality videos. And so it turns out that adapting the video generation for this task is actually quite important. And there are two ways of doing that. We can do joint training. So we take the RoboCasa demonstrations, we fine-tune both the video and the action. And that interestingly works worse than if we do two-stage. So we first fine-tune the video generation, and then we freeze it, and then we fine-tune or we train the action generation. We found that the two-step way of training actually works better, which is quite interesting. We also looked at video prediction horizon. And it turns out that across all the different thresholds we looked at, if we increase video prediction, the quality of the action generation increases, and we measure that by success rate on the y-axis. And in all of these cases, we kept the action prediction horizon fixed to 0.8 seconds. And this highlights the importance of modeling dynamics accurately and the interplay between dynamics and action. We also looked at using action-free data. I think this is probably the most exciting result. So we have 24 tasks in RoboCasa, and what we did is we split this set into 12 and 12. We trained the video generation on all 24, as we did before, and then we trained the action generation just on the first 12, and then we evaluated on all of them. And we saw that there wasn't much of a performance drop. So even though we didn't train on all the tasks, we could get generalization to the unseen tasks out of the box, which is very exciting because it highlights the ability to use action-free data to learn priors, which then transfer to actions. So we looked at this a couple of tasks that we hadn't trained on and we evaluated on: turn, sync, spout. Again, you see the video prediction on the bottom and then the actual rollout on the top. So this is something that we haven't trained on, but it's generalized quite well too. We also looked at pick and placing to counter. There's lots of different ones that we checked. The interesting thing is we haven't trained the action predictor on these, but nevertheless, it kind of worked out of the box via transfer from the video backbone, which is very exciting. Oops. Okay. We also looked at the quality of video prediction with respect to action success. So it turns out that there's a strong correlation. If the video prediction metric indicates high quality video prediction, that correlates with successful rollouts, which is exciting because it means as these video models tend to, as they will get better and better, which I'm sure they will, we should be able to leverage that for action prediction. Okay, we also did a few real-world experiments. So this is early stages. We collected data, 200 demonstrations for a few different tasks. Maybe I'll go quickly through this. We put together a set of 5 tasks: open drawer, pick and place, put M&Ms in cup, upright objects, stack ups, just to basically understand what kind of transfer we get from these video backbones in the real world in addition to simulation. We controlled the training conditions, and then we have sort of separate testing conditions that I can go into the details offline. And what we really wanted to study here is generalization. So do we get the same kind of transfer from the video backbone in the real world as we saw in simulation? And we looked at a few different axes. We varied the object location. We looked at new objects. Can we manipulate them? We looked at unseen backgrounds and so on. And indeed, we get similar kind of transfer to what we measured in simulation. And the robot is able to manipulate unseen objects, which is something that we hadn't seen before. It can adapt quite well to unseen backgrounds and so on. And here are a couple of very quick examples. So in this setting, the robot is going to pick an object that it hasn't seen during training and then put it in this bin, in the cup. Okay, and similarly, we'll do the same with an unseen background. Hopefully it's going to play, yes. So the background is different, and we get this kind of adaptation despite the fact that we train on sort of few demonstrations thanks to the power of the pre-trained video backbone. With lots of these videos for all of the tasks, and we describe in detail the test and training configurations. Okay, so to very briefly conclude, we looked at LBMs, and we saw that the way we train them and the way we evaluate them, we're starting to see that they enable dexterous manipulation on more and more complex and long horizon tasks with some limitations. So we need to do this fine-tuning step. I didn't go into the details of evaluating them zero shot, but there are some limitations there. And we're looking at ways to overcome those, both to improve the success rate and also to get this kind of generalization outside the things that we trained or fine-tuned on. And for that, we looked at structured foundation models. And in particular, we saw that video generators are robust policies. So sort of out of the box, they encode very powerful priors. And when we fine-tune them with actions, we get them to perform well on the tasks that they're fine-tuned on, and also generalize to things outside the training set, which is very promising future direction that we're working on integrating into the main LBM system and exploring further. Okay, thank you very much.
Thank you, Rareș, for the great talk and for sharing some of your recent results. Any question from the audience?
I think I'll go for the kind of more higher level. I think you're probably the person I've seen the most do demonstration, learning from demonstrations, and like a really wide variety, and then you're doing long term. What's your take long term for robotics? Is this how you're thinking about we're gonna go about and have robots in our house? Is it all based on demonstration? Like, what's your ideal model, like system model you would like to see?
Yeah, okay, let me repeat the question. So how do I think about getting robots in the homes, and what's the path to getting us there? Is it scaling up demonstrations? Is it something else? Yeah, I mean, there's a lot to say to that question, but I think it has to be a combination, right? I think we definitely, so first of all, I think if we want to have a robot work really well for a particular task, right, to get a specialist, I think we probably have to train a generalist first on many tasks and then do adaptation on any one particular task. And that's going to have a higher chance of success than just, collecting 10,000 demonstrations for just one thing, because that's going to be very brittle. And then in terms of sort of general purpose robots, I think scaling the data is important. So diversity of tasks, I would say, much more than, task specific data, and also borrowing priors from things that we have seen sort of work. So from existing foundation models, right? So language models, vision language models, video models, they encode quite a bit of interesting information and generalization in terms of semantics. And I think that also has to be an ingredient. So a combination of real world data, I think diversity is important, as well as pre-trained models that we've seen, actually can do quite some interesting things.
Thank you. Maybe one last question while the speakers reach slowly. Please, I invite all the speakers to join for the panel discussion while we get the final question.
Yeah, great talk. I watched that the bike wheel, experiment. I watched it live when the robot was succeeding. It was really cool. So
Yeah.
way nicer than watching these videos. So I have a question about that. Oh, it was actually important that we see the slides.
Sorry. Okay. Now that's going to be difficult. We might have to wait.
Okay, whatever.
We might have to wait 10 minutes to set up the. Let me see.
It's fine. It's fine. Okay. So it was okay.
Okay, we're back.
So there was like a slide on the success rates.
Yes.
And I noticed that, like, when it comes to the bike wheel experiment,
Yeah.
it looks like the specialist is better than the fine-tuned LBM. Is that true? Like the leftmost?
Yeah, so it's difficult. Yeah, it seems like based on just the average of the violin plot, one seems higher. I forgot to mention, thank you, okay, this is good. The letters indicate whether the two are separable with statistical significance. It's based on a sequential A/B test. So actually, despite the fact that it looks like one is better, we can't really say with 95% confidence whether one is better than the other. But it does happen. So the LBM method isn't always better. It does happen that sometimes just fine-tuning, just the single task method is better. It depends on sort of the diversity of the task and how we evaluate. And this one is kind of, like it's long horizon, it's dexterous, but the wheel is there. There isn't a lot of diversity in terms of, at least not in the way we evaluated, right? A lot of diversity in terms of distractor objects and things like that. It does happen. So we're trying to understand why.
All right. Okay, thanks.
Let's thank again our speaker.
Thank you.